Okay, in our previous lecture, we discussed about the basic properties of a coding scheme should have. We discussed that every coding scheme should avoid baseline wandering. It should avoid the DC components. It should have immunity to noise and interference, should have error detection as well as error correction. It should not be complex. It should have self-synchronization, etc. Baseline wandering is simply the difference in voltage of a bit as compared to average voltage of the signals in that scheme. DC components mean small frequency components should not be present. Self-synchronization means the clock of a sender and receiver should tick at the same time. If there is error in the clock of sender or the receiver, the data will be misinterpreted. The error detection should be there in the coding scheme, as well as error correction should be there in the coding scheme. The coding scheme should have immunity to noise as well as interference from other surrounding signals or electromagnetic radiations. It should have less complexity. It should have least number of circuitry. In this table, we compared the key data transmission terms, the bit rate, the baud rate, what is data element, what is data rate, what is signal element, what is signal rate, etc. So let us start today's lecture. So if we talk about the coding scheme, each coding scheme should have certain conditions that should be met. First, receiver must know the timing of each bit. The receiver must know some accuracy when a bit begins and when a bit changes or ends. The second requirement is that the receiver must determine whether the signal level for each bit position is a high or a low. So every coding scheme has its own way of starting the voltage level, ending the voltage level, which voltage level will represent a 0, which voltage level will represent a bit 1. So these things vary from scheme to scheme. But what remains constant is that every bit will be represented by a voltage level. That is certain, that is fixed. But how it will be represented, low or high, low voltage or high voltage or reverse, etc. These are the secondary things. The primary thing is that every bit will be represented by some voltage level. The second thing is important, that a very good coding scheme should avoid baseline wandering, should avoid DC component, should have self-synchronization capability, should be immune to noise, should be least complex possible, etc. So we will move to now the coding schemes, and one by one we will discuss them. So some of them are the old schemes, some of them are the new scheme, some are obsolete today, some are in use today. So we will start with the oldest techniques which are obsolete nowadays, which are not used. But to understand this coding, we start with the oldest one. And every coding scheme should satisfy the few parameters which I have discussed. I am repeating them once again for you. So every coding scheme should have baseline wandering, solving capability, It should avoid the DC component. It should have self-synchronization clock of the receiver as well as the sender. It should have built-in error detection as well as error correction. It should be immune to noise and interference. It should be least complex possible. So there are 5 types of broad categories of coding schemes in which we can divide different coding schemes. The first one is the unipolar. We will discuss it later. On the next slide, let us first discuss the 5 broad categories in which we can divide the coding schemes. So the line coding means if we have a stream of bits, zeros and ones, then each bit will be coded accordingly in the sequence, in the line. So that's why they are called as line coding. Means you start from the extreme left of the line and you go up to the extreme right of the line by coding each bit with some voltage level. So the 5 categories in which we can divide the different coding schemes are the unipolar. It has only one coding scheme, which is called as NRZ. NRZ means non-return to 0. Polar coding scheme, it has 4 different coding schemes: non-return to 0, return to 0, biphase Manchester as well as differential Manchester coding schemes. NRZ can further divide it into 2 categories: non-return to 0 level and non-return to 0 inverted. Bipolar has 2 coding schemes, AMI and the pseudo ternary. Multi-level has 2B, 1Q, 8B, 60 and 4D PAM 5. Multi-transition has MLT 3. In our syllabus we have these coding schemes: unipolar, polar and bipolar for the digital data and digital signal coding schemes. However, we will superficially also discuss the multi-level and multi-transition coding schemes as well. So now let us start with the first coding scheme. The first coding scheme is NRZ, which means non-return to 0. Non-return to 0 what? What should not return to 0 is the voltage level. And each voltage level will represent a bit. How it represents? Here positive voltage is defined by bit 1 and a 0 voltage defines a bit 0. It is called as non-return to 0 because the signal does not return to 0 at the middle of the bit. Whereas you will see in various other schemes that the signal will return or voltage level will return to 0 in between the bit coding. That is, it may pass the negative, it may cross the time axis and may go to the negative axis, it may come to 0 in between. But if you see the diagram of unipolar NRZ scheme, we can clearly see that this is the reason in which a bit 1 is defined. Here, the high voltage level is representing a bit 1, and this voltage level is flat and constant until we have a second bit which is 0, and 0 is represented by a low level. So here the signal or voltage level is not returning to 0 in between the bit level. Next is 1, which is again represented by voltage level, constant voltage. Next again 1, which is again represented by a constant voltage level, high voltage level. Then we have a 0, which will be represented by a 0 voltage, and it touches the time axis. The power is half V square for bit 1, half 0 square for bit 0. So in total, the power is half V square in NRZ scheme. When we compare the NRZ with its polar counterpart, it is a unipolar scheme, then we find that it is costly as compared to its polar counterparts. So here we also, in the next scheme, we will compare the power consumption. Power consumption is also large in case of unipolar NRZ as compared to other. So this scheme is an obsolete scheme which is not being used nowadays. Its counterpart is the polar scheme, in which we have the voltage levels which are on the both sides of the time axis. Means a bit 0 or 1 can be represented by a voltage level, and it can cross the time axis. So the voltage level will be present on both sides of the y-axis. It will be above the time axis as well as it will be below the time axis. So this scheme can further be divided into two parts. NRZ L means NRZ level, NRZ I means NRZ inverted. So how these two schemes are different? In first scheme, that is NRZ L means level. So the level of the voltage will determine the value of the bit. In second scheme, that is NRZ invert, here the change or lack of change in the level of the voltage will determine the value of the bit. So the main focus of all of us in coding schemes is to study which voltage level is representing a bit and how it is representing a bit. So in NRZ L level will decide the voltage whether it is a 0 or 1. NRZ invert, here the change or lack of change in the voltage level will decide the value of the bit. In this scheme, if there is a no change in the level, the bit is said to be a 0. If there is a change in the level, the bit is said to be 1. In NRZ level L, we can have a high level representing by 1 and low level represented by a bit 0. Now let us see with the help of a pictorial diagram, and let us clear this how the things are working. The first graph is the NRZ L, and the second graph is for the NRZ invert. So here you can see the voltage level is deciding the bit, and here the 0 bit is represented by a high voltage. We have already discussed that it depends upon the scheme. One scheme may use a low level to represent a 0 bit. The another scheme may use another level to represent another bit. So here the bit 0 is represented by a high voltage level and a bit 1 is low level. And further, this is a scheme in which the voltage levels can cross the time axis. They are present on the both sides of the time axis, that is y-axis positive, y-axis negative. So in NRZ scheme, a 0 bit will be represented by a high level and a bit 1 is represented by a low level. Similarly, next is a bit 0, another is a bit 0, so both are represented by a high level. Then we have consecutive 3 ones. So each one bit will be represented by a lower level, and again we have a bit 0 which will be represented by a high level. So in this diagram, a 0 bit is represented by high voltage, a 1 bit is represented by a low voltage. Further, the voltage levels cross the time axis. That's why it is called as bipolar, non-return to 0. And here level is deciding the bit. That's why it is called as non-return to 0 level coding scheme. It is a bipolar coding scheme. The second one is non-return to 0 inverted. Here we have to understand, it is a very difficult or complex idea to understand. Here this blank dot represents there is no inversion, whereas this solid black dot represents the inversion, that is next bit is 1. So here the first bit stream is 0, which you can see from the above graph. So it is represented by a flat. Next bit is 1. So the voltage level will change when a bit changes. So the first change is at 1. For 0 bit, the voltage will remain constant. Again we have a 0, the voltage will remain a constant. Then we get a 1. Voltage should change because we have moved from bit 0 to 1, so it changes. Again, if bit 1 is obtained, it again changes. Then we have a consecutive third one, again the bit will change. So what I am trying to say is, the axis will change only when a bit 1 is there. Means we started with a bit 0, we had 1. So obviously the voltage should go to another polarity. Then we have a 0, polarity will not change. Then we have again 0, polarity will not change. Then we had a 1, polarity will change. Then we had another 1, again polarity should change. Then we have a third one, again polarity should change. After 1, the last bit is 0. So it is already at high level due to this 1. So it will remain at. So in non-return to 0 L, the level of the voltage will determine the value of the bit. In NRZ I invert, the inversion or the lack of inversion will determine the value of the bit. Here the average power is N by 2. Bandwidth is F by capital N. R is the number of voltage level which represents a bit. That is people vehicle analogy. One people in one vehicle means R is equal to 1. One voltage level represents 1 bit, means R is equal to 1. So here in both the schemes, one voltage level is representing only 1 bit. That's why R is equal to 1 over here. So it is all what I have to teach for today's lecture. We have studied the polar and unipolar and bipolar coding schemes, that is NRZ, NRZL, NRZI, and how they lack and what are the disadvantages we will study in the next lecture. Obviously, the disadvantages will be the